Welcome back to the first course in general physics with part 3 of the subject dealing with the motion of a system of particles. In this lecture, we will continue talking about the linear momentum for a system of particles, and we will see the connection between the linear momentum, the rate of change of the linear momentum, and the external forces acting on it. We will then move to talk about the conservation of linear momentum, derive this important principle. After that, we will move on to discuss collisions, a special case of the interaction of two or more objects. And in this regard, we will consider the concept of impulse that takes place during the interaction of two or more objects with each other. We will derive the conservation of momentum from the definition of impulse and the consideration of Newton's laws of motion. And finally, we will discuss the problem of elastic collision between two particles in one dimension. And we will hopefully have enough time to arrive at the evaluation and determination of the relative velocities of the two particles and see how they are related before and after the collision takes place. Let's remind ourselves that the linear momentum for a system of particles have been developed in the previous lecture, and we noticed that the total momentum P capital of a system of particles is equal to the total mass of the system capital M times V center of mass. Let's keep that formula in mind. And for a closed system, meaning a system which does not change mass, no mass enters the system, no mass leaves the system. For such a system, if we derive the two sides of this equation that we just mentioned, P capital is equal to mv center of mass, we derive it in both sides, we will get on the left-hand side dp by dt, and on the right-hand side we will get m times dv center of mass by dt, or ma center of mass from the definition of the acceleration. That tells us that the rate of change of the total momentum of a system of particles is equal to the total mass of the system multiplied by its center of mass acceleration. And from Newton's second law for a system of particles that we just mentioned previously, which states that the summation of the net external forces acting on the system is equal to the total mass of the system multiplied by its acceleration, the acceleration of its center of mass. Coupling these two together, we will obtain the result that dp by dt for the system of particles is equal to the summation of the external forces acting on the system. And this formula majestically resembles the formula for the general form of Newton's second law as applied to a single particle. So again, we conclude that the center of mass of a system of particles moves in exactly the same way as under the influence of external forces as if the total mass of the system were concentrated at that special point, which is the center of mass. And that point moves in space as a particle, a single particle, under the influence of the external forces. From this concept and this principle, from this general law of Newton's, the general form of Newton's second law of motion, which states that dp by dt equals to the summation of the external forces acting on the system. From this, we can arrive at the important statement, which is the principle of conservation of linear momentum. How do we arrive at this important formula or important principle? We just have to remember that, as we mentioned, dp by dt is equal to the summation of the external forces acting on a closed system. And if we have the special case where the net external forces acting on the system is 0, if we have no net external force acting on the system, then the right-hand side of the equation is 0, and thus dp by dt is equal to 0. And from the definition of the derivative, if the derivative of a quantity is 0 with respect to time, that means that quantity is constant with time. So if dp by dt is equal to 0 because the external forces are equal to 0, or the summation of the external forces on the system is 0, then the momentum, the total momentum of the system is equal to a constant as far as the system is closed, meaning no particles enter it, no particles leave it, no mass change of the system. So this formula, P is equal to constant for an isolated system which is not acted upon by any external force. That's what isolated is. And for a closed system which does not change its mass with time. This implies that if we look at a system at any point in time, call it initial time, the linear momentum of the total system, of the whole system, it would be constant, meaning at any later time, call it t final, at any later time, if we measure the linear momentum of the system, we will find it to be exactly the same as the initial momentum that we have measured previously. And equal, we mean by equal in magnitude and in direction. So the momentum of a system of particles is fixed both in magnitude and in direction in space. It does not change. That is true for a closed and isolated system. This is the principle of conservation of linear momentum. This conservation law, or important principle that we just arrived at, is actually more general than Newtonian mechanics itself. It could be surprising, but it is a very basic law that governs the motion of systems. It is more general than Newtonian mechanics in a sense that it is applicable even in the regime of velocities of our systems where Newtonian mechanics breaks down, where Newtonian mechanics does not apply anymore. We know that as the speed of a particle grows and increases to the point that it might reach the region of the speed of light, then Newtonian mechanics breaks down. Newton's laws do not apply anymore in their form. And yet, even in that region of velocities, the conservation of momentum applies. So it's more general than Newtonian mechanics in that sense. This is also a vector equation, as we just mentioned, and it applies to the three components of motion. So we can conclude that if the summation of the external forces is equal to 0 in a given direction, if that component of the external forces is 0, then that component, that particular component, the corresponding component of the total momentum, linear momentum of the system is conserved. So, for example, if we have a case where the summation of the x component of external forces acting on a system is 0, while the others are not, then we can conclude that only the linear momentum in the x direction is conserved. P sub x is conserved, while P sub y and P sub z are not conserved. So in that sense, we can apply this law of conservation of momentum in three equations and look for whichever has zero external forces, and we can apply the conservation of momentum to it. Now we move to a special type of interaction between two or more objects, which is the topic of collisions. This is a special type of interaction between objects, and we can define it vaguely as the interaction in which two or more bodies exert a relatively large force on each other, strong force on each other for a short period of time, relatively. Such an interaction between objects where they exert very large force on each other during a very short period of time, we call it collision. It might occur to us that in a collision, the two particles must get in contact. They must touch each other. But in our more general definition and more precise definition of collision, the two objects are not necessarily in contact during the collision. So, for example, if two charged particles approach each other and they scatter after they approach each other, although they don't touch each other, we can call this interaction between them a collision between the two particles, even though they don't touch. They interact through a long-range force. So contact is not necessary in the collision process. During contact or during the interaction, whether it is contact or non-contact, we can define a quantity called the impulse. Suppose that we have two objects that are interacting, that are colliding. The forces of interaction between them, each one of them, of course, exerts a force on the other, and the force exerted by one on the other which is equal in magnitude and opposite in direction to the force that the second one exerts on the first one, this force varies in magnitude with time in general. It's not the same. Like if you throw a baseball against the wall, the force at the initial moment where the ball touches the wall, the force is zero of interaction between them. And as the ball is compressed against the wall, the force of interaction grows more and more until it becomes maximum when the ball gets to a momentarily rest state where its velocity becomes zero momentarily, and then it starts rebouncing back. At that moment where it reaches a zero velocity with respect to the wall, at that moment we have a maximum a maximum force of interaction between the wall and the ball, and then it goes back where the force starts decreasing from this maximum value down to zero as the ball leaves the wall. This is an example of the interaction where the force is a contact force. And but all that we need to know is that the force varies with time, and it is exerted by one object on the other and by the other on the first object during a short period of time. And this is a demonstration of the collision of two objects, for example, and the force between them is demonstrated by this straight line, border line between them, because it squeezes both objects as a result of the exerted force. And we call these two objects the R object, which is the right-hand side object, and the L object, which is the left-hand side object. And we notice that in this collision, the L object acts on the R object by a force f of t in a sense that it varies in magnitude with time, and the direction of that f of t acting on R is to the right, and similarly the object R exerts a force on the left object, and that force is minus f of t, indicating that this reaction force is an equal force in magnitude, and it is in opposite direction, as the figure shows. Now, this figure demonstrates two examples of how could the force of interaction vary with time. The curve on the left-hand side, this pink curve, shows a particular curve where the force varies with time, and the initial time, at initial time the force was zero, and at the final time the force the force was also zero, and in between the force reaches a maximum and starts going down. Now, the time of interaction between the two objects is delta t, which is t final minus t initial, and the shaded area under the curve is what we call J, the impulse that acts on the on one of the objects, the impulse that is exerted on one object due to the force applied to it from the second object. And that impulse, we will come to define it in a more rigorous form a little bit later, but all that we need to know for the time being is the impulse is the area under the curve, and if we can find if we can find between T initial and T final a rectangle that has an area that is equal exactly to the area under the original curve, then we can say those two areas are the same. Then the rectangular shape is a convenient way to measure the impulse acting on one of the two objects, because the area of a rectangle is easily determined by the multiplying the height by the value of delta t. And the height in this case, we call it F average. So the height of the rectangle is the average velocity. So in a sense, if we multiply the average velocity, the time weighted average velocity acting on one of the objects, multiply it by delta t, that will give us the area under the curve, which is the impulse. That is in a graphical form. That is the definition of the impulse in a graphical form. And in a more rigorous mathematical form, this area under the curve is derived or is defined as the integral from the initial time to the final time of the function of t, of the force that is a function of t, f times dt. This integral is simply the impulse that acts or that is exerted on the right-hand side object. This is a vector equation, and the area is a scalar quantity. The area that we talked about is a scalar quantity. So in fact, the magnitude of this integral is simply the magnitude of the area under the curve that we spoke about, and the direction of the impulse is the same as the direction of the force exerted on the body. So for example, the impulse exerted on the right-hand side object is directed towards the right because the force exerted on it is towards the right, and the impulse that is acting on the left-hand side object, which is J sub L, is to the left because the force exerted on the left-hand side object is to the left due to the interaction of the two bodies. So this is a statement that can be derived directly from Newton's second law applied to the right-hand side, to the right-hand object R. And if we apply that second law in its most general form, we obtain the result dP of object R is equal to F, the force acting on object R, times dt, because the definition, as we noticed, for the force acting on the object is simply the rate of change of its momentum. So if we assume that these two objects which are interacting form a closed system and isolated system where there is no external force acting on the system, the only forces acting on each particle are the internal forces, then in Newton's second law, F would be simply the force of interaction between the two particles, F sub r only, and that is dP by dt is equal to F sub r. That is from Newton's second law, and we have to compare now between these two formulae. Notice that F sub r dt is the same as in the above equation on the right-hand side. Now, if we integrate this second law of Newton, this form of Newton's second law, which derived from second law of Newton, if we integrate both sides, on the left-hand side, we will get the integration of dp, which is simply p from p initial to p final, from the initial time to the final time, which is simply p final minus p initial. That's the integration of the left-hand side quantity. And the integration on of the right-hand side quantity is simply f sub r dt, which is j sub r, which is the impulse. And that way we get a relation between the change of momentum of the object r and the impulse acting on that object. So delta p, or p sub r in the final state minus p sub r in the initial state is equal to the integral of f sub r dt from initial time to final time, which is simply the impulse acting on object r. So delta p, the change of momentum in object r, is equal to the impulse acting on object r. Similarly, the change in momentum of object L is equal to the impulse acting on object L. We have to remember that the impulse is simply the force times time integral. The force is the one that determines the direction. And since those two objects are interacting, then the force of interaction, according to Newton's third law, is equal and opposite on each one of them. And thus, we notice, or we realize, that the impulse acting on R object is the same as the impulse acting on L object, but opposite in direction. The two impulses are the same, but they are in opposite directions. That is a result of Newton's third law of motion. And this we can conclude again the conservation of momentum for an isolated and closed system from this definition of the impulse and its relation with the momentum change. Because if we look at the two objects now together and we ask ourselves about what is the total momentum of the system and what is the change in that momentum of the system. So the total change in momentum for the system consisting of the two interacting objects L and R is equal to delta P sub R plus delta P sub L, and that is equal to J sub R plus J sub L. Remember that the J's are vectors and J sub R is equal in magnitude to J sub L but opposite in direction. That means J sub R plus J sub L is equal to 0, and that means delta P sub R plus delta P sub L is equal to 0, which means delta P total for the total system consisting of the two objects, delta P total is equal to 0. That means P initial is equal to P final for the system. This is the principle of conservation of momentum for the system of colliding objects. Notice that this principle is derived regardless of how they interact, regardless of the time of interaction, regardless of the type of interaction. So this conclusion is a very general conclusion to colliding objects. So that means we apply this principle of conservation of momentum to the collisions all, regardless of their type. This is an important statement. And now we talk about another principle during the collisions. So far we have reached a conclusion that during collisions, momentum, the total momentum of the system is conserved. The momentum before collision is equal to the momentum after collision. What about energy? Is energy conserved or not? This is another quantity, another important quantity in physics. We realize experimentally that there are two types of collisions. One of them we call elastic collisions. These collisions are the collisions which conserve energy, meaning if the energy of the system before collision is equal to the mechanical energy of the system after collision, then we call this collision elastic collision. So elastic collisions do conserve energy. Conservation of energy is applied to such collisions. So in elastic collisions, we have the two principles are applied: conservation of momentum and conservation of energy. In general, conservation of momentum gives us, in general, three equations because we have three components, and conservation of energy gives us only one component because it is a scalar equation. So in general, we have, in the most general form, we have four equations, so we can solve for four unknowns. If we have a problem with four unknowns in a collision, we can solve it using conservation of momentum and conservation of energy in the case of elastic collisions. We have the second type of collisions, which are the inelastic collisions. Inelastic collisions do not conserve energy. So in an inelastic collision, we encounter an energy loss due to the collision. The initial energy is different than the final energy, meaning the energy before collision is different than the energy after collision. So we have to keep those key points in mind, since in applying the principles, the general principles to collisions, we will be using these principles often. Now, let's take an example, a particularly simple example of an elastic collision in one dimension. This is the simplest case of collision where the two objects collide head-on, meaning they start motion along a straight line, they collide, and then they keep going on the same straight line, back or forward, it doesn't matter, but they have only one component of motion. That is the collision in one dimension, or one-dimensional collision. Let's take the elastic case where, as we noticed, as we said, in the elastic case, the energy is conserved. Now, in this collision, we have a projectile body or ball, which we treat as a particle moving with initial velocity v1 sub initial. It has mass m1, and there is another ball, which is the target ball, with mass m2, having velocity v2 sub initial, and both of them supposedly are moving along the x-axis. The one dimension on which the collision occurs, we call it the x-axis for convenience. It's just a name that we give that axis. So this is the configuration, and this is the state of the two objects or the system of particles that are colliding. This is their state before the collision. Now, after the collision, we have the particle with m1 will be moving with v1 final, and particle number 2, the target particle, would be moving with v2 final, and we assume that they move along the x-axis also. And so in this case, we have a one-dimensional case, and we assume that the collision is elastic. So in an elastic collision, in one dimension, we encounter the conservation of momentum as usual, because momentum is conserved in all collisions, and we encounter the conservation of energy also. Energy is conserved. Since we have one-dimensional motion, then the conservation of momentum gives us only one equation, which is in that dimension of motion, the x dimension, as we called it. And the conservation of energy gives us one equation because it's a scalar equation. It's just one, doesn't have components. That means we will have a total of two equations in this problem. These two equations are just sufficient to solve the problem if we only have two unknowns. If we have more than two unknowns, we cannot solve the problem. If we have one or two unknowns, we can solve it easily. Actually, if we have one unknown, we have to use only one of these equations, and we solve that unknown for that unknown. If we have two unknowns, we have to use these two equations and couple them together, and we will find the solution. So as we just said, two equations, and those two equations, we have to stress that they are independent equations, because where the conservation of momentum is coming is completely different from where the conservation of energy is coming. So these two equations are independent, and thus they allow us to solve for two different unknowns of the motion. So from the conservation of momentum, the first principle, we have m1 times v1 initial plus m2 times v2 initial, which is the total momentum of the system before collision in the initial state, is equal to m1 v1 final plus m2 v2 final, which is the total momentum of the system after collision in the final state. Notice that here in this equation we have used the symbols for scalar quantities, because as usual we are dealing with motion in one dimension. So in that sense, the direction of the vector v is determined by the sign of v. So if we have v a positive quantity, then we say that v is in the positive x direction. And if v, any of the velocities, has a negative sign, then we say that the direction of v is in the negative x direction. So the sign is enough to determine the direction of the motion of any of the two objects before or after the collision. And thus we use this symbol which is characteristic for the motion in one dimension. And secondly, we apply the principle of conservation of energy to the system, because the collision is elastic, and in this case we have the kinetic energy of the first object 1/2 m1 v1 initial square, which is the initial kinetic energy of the projectile object, plus the kinetic energy of the target object, which is 1/2 m2 v2 initial square. This is the summation of the energy of the kinetic energy before collision. That's equal to the summation of the kinetic energy after collision, which is 1/2 m1 v1 final square plus 1/2 m2 v2 final square. This is a consequence of the fact that the collision is elastic. So we have those two equations, and we notice that we can couple these two equations and solve the problem if we have two unknowns, as we mentioned. However, the solution of these two equations might look somehow awkward or algebraically a little bit difficult, because one of the equations contain quadratic terms in velocity square. It has velocity square. It is easier always to deal with linear terms like equation like the upper equation, which contains velocities to power 1. And in this sense, we can couple these two equations and combine them together and get a different equation from the combination of the two, which is linear in velocity. And this equation, which is a resultant of the coupling or the combination of the two previous equations, gives a formula for the relative velocities of the two objects. And this states that v1 initial minus v2 initial, that's the relative velocity of the two particles before collision, is equal to the negative of v1 final minus v2 final. v1 final minus v2 final is the relative velocity of the two particles after collision. So this statement, this algebraic statement, tells us that the relative velocity of particle 1 relative to particle 2 before collision is equal in magnitude and opposite in direction to the relative velocity of particle 1 relative to particle 2 after collision. Opposite in sign because it's coming from this negative sign before v1 final minus v2 final. This negative sign implies in the opposite direction because the velocities, as we know, are vectors. So the negative means opposite direction. So this is the relative velocity between the two objects. Relative velocity before collision is equal to the negative of the relative velocity of particle 1 relative to 2 after collision. This is a linear equation in velocities, and we can use it instead of the conservation of energy. Notice that so far we have three equations, but they are not all independent. They are not all independent. This third equation is derived from the coupling of the two equations, so it's not independent. So it should, if we want to use it, it should replace one of the two basic equations. So we can use it instead of the conservation of energy in case if we don't need energy. If we don't need to evaluate energy, we can use this instead of the conservation of energy formula, because that conservation of energy involves quadratic terms in velocity, while this involves linear velocities, which makes it easier algebraically to solve the equation. So we can use the conservation of momentum, which is linear in velocities, and we can use this equation, which is linear in velocities. And those are the two equations that we can use to solve the problem. And as we said, this equation is important in our solution because if we have, for example, if we know three velocities, initial velocities, for example, of the two particles, and one of the final velocities of one of the two particles, we can evaluate the velocity of the fourth immediately from this formula, directly, without going into any more details of the calculations. And also, as we noticed, as we said, it is linear in velocity, and in this sense, it makes it easy for us to solve and to couple the two equations, which is the one that is arising from the conservation of momentum, and this one to solve the problem and find any two unknowns of the motion of the system of particles after collision. And at this moment, I would like to finish this lecture, and thank you for your attention.